Hi Year 12, I hope you're all well. Right, since the last task that I assigned to you last week about the rate of hydrolysis of haloalkanes, I've had a few email queries about tasks 10 and task 11. So I thought before I set you a new task, I'm going to quickly go through these two, okay? So task 10 says, write an equation for the reaction between 1-iodobutane and aqueous dilute potassium hydroxide and name the organic product. And it says, for the reaction above, state the observation with aqueous silver nitrate, and when carrying out an experiment to compare the rate of hydrolysis between a chloro, bromo, and iodo haloalkane, discuss any factors you'll need to consider. So, what's really important in a wordy question like this, and this crops up in exams all the time, is that you're quite methodical in ensuring that you tick every box, that you do everything the question says. So it starts off by saying, write an equation for the reaction between 1-iodobutane and aqueous dilute potassium hydroxide. So let's do that first of all. So 1-iodobutane, meth, eth, prop, but. So let's have our iodine on the end there. We're reacting it with dilute potassium hydroxide, so I'm going to add a KOH. Now this is going to undergo a nucleophilic substitution, so the hydroxide ion is going to kick out the iodide. So we're going to end up with the alcohol CH3, CH2, CH2, CH2OH. And then the iodine, which will have been kicked off as an iodide, will be floating around as an iodide ion, and plus we'll also have a potassium ion, which was released from that. So that's one option. You could also have the same equation, but ignoring the potassium. Remember, we call this a spectator ion. It doesn't really do anything, so it's perfectly justified in not including it in the equation. So you could have CH3, CH2, CH2, CH2I, plus OH minus, make sure negative charge and lone pair on the oxygen of the OH, and that's going to give us CH3, CH2, CH2, CH2OH plus I minus. Okay, so exactly the same equation, just ignoring the potassiums. Note that I've used a structural formula in these. I have not used a molecular formula of C4H9I. And that's because even though that is the correct molecular formula, you can't tell that that molecule is 1-iodobutane. For all we know, that could be 2-iodobutane, or it could be 2-iodo-2-methylpropane. It could be one of the isomers of that. So whenever you're doing equations like this, always use a formula where you know that the structure is absolutely clear. Okay, so we've done the first bit of the question. Name the organic product. We need to do that now. Meth, eth, prop, but, and it's got an OH group. So this is butan 1-ol. So we've done that bit. For the reaction above, state the observation with aqueous silver nitrate. Now, silver nitrate, AgNO3, that is our chemical test for halide ions, for chlorides, for bromides, for iodides. In this reaction, iodide ions are released, so that means we are going to get a yellow precipitate. Okay, and then finally, when carrying out an experiment to compare the rate of hydrolysis between chloro, bromo, and iodo haloalkanes, discuss any factors you would need to consider. What this is asking us for are control variables. So if I had a beaker with 1-chlorobutane, a beaker with 1-bromobutane, and a beaker with 1-iodobutane, and I wanted to time how long each one took to react, then there's certain things I need to do the same in every single reaction if the results I get are going to be a fair comparison, a fair test. So factors are things like same amount, really I should say mass or volume of haloalkane, same volume of silver nitrate. I want them to be the same temperature, same amount of stirring, that sort of thing, okay? Because let's say I carry out these reactions in 3 different haloalkanes, but one of them is warmer than the others, that one's probably going to react the fastest. And it's not actually telling me it's reacting faster because of the halogen, it's reacting faster because of the temperature. So this is not an exhaustive list, this is not everything, but these are the sort of things that you would expect to come up with. Okay then, moving on, task 11. So this is the one which caused a few more issues. So describe and explain the hydrolysis of chlorocyclopentane and bromocyclopentane with aqueous potassium hydroxide. In your answer, include one equation including the structure of the organic product. So let's do that first. Now I'm going to use skeletal formula here. You could use display formulae, I don't mind. But again, your formula needs to be clear about what the structure is. So that's my cyclopentane. If it's chlorocyclopentane, I need to have a chlorine on there somewhere. It's with potassium hydroxide. I'm just going to add the hydroxide ions on this time. I'm going to forget the potassium. After the substitution's taken place, I'm going to have my hydroxide ion on there, and my chloride ion will have been kicked off. It says one equation, so I could have done this with the bromocyclopentane if I wanted as well. That would have been fine. Indicating the structure of the organic product. The structure is a bit vague. If it had said displayed formula, I'd have to draw this out with every single bond. Because it wants the structure of the organic product, that would be absolutely fine. The reaction mechanism, right. So this is your standard nucleophilic substitution. I'm going to draw it out using a display formula here just to be absolutely complete with it. So I've got my chlorine, OH, negative charge, lone pair. So remember your basics. With your hydroxide nucleophile, the negative charge and lone pair both have to be on the oxygen. Okay, I can't have a negative charge over here, that would be wrong. Mark number 1, attacking this carbon because it's slightly positive. The reason why it's slightly positive is because this chlorine is more electronegative and withdraws electrons towards itself. Mark number 2, I break this carbon-chlorine bond onto the chlorine. Okay, you don't get marks for the delta pluses and delta minuses, but it's often worth putting them in anyway. Then, let's get to our product. This mechanism is one of the most straightforward because it's a one step, there's no intermediates, there's no halfway points, it just goes from the reactants on the left hand side to the products on the right hand side. So now I've got my OH group there and my chloride ion has been kicked off. Okay, so one equation showing the organic product, the reaction mechanism. Right, this question here is one which has stumped quite a few of you, and I can understand why it has, because I've not actually explained this one to you yet. So there's 2 types of ways of breaking bonds, okay? I'm going to explain both of them, but then I'll explain which is the one which applies here. The 2 methods of breaking bonds are known as homolytic fission and then heterolytic fission. Okay, so these are the 2 different types. You've encountered them both already, you just haven't known what their names are. So let me explain homolytic fission to begin with. You've encountered this in your free radical substitution mechanism. During the initiation phase of a free radical substitution, where you've got your halogen and you have UV light and it splits up a halogen to form 2 free radicals, the following happens. This covalent bond between these 2 chlorines is a shared pair of electrons. The definition of a covalent bond is that it is a shared pair of electrons. And during homolytic fission, one of the electrons from the bond goes onto the chlorine that the electron belonged to in the first place, and the other one goes back to the other chlorine. Okay, so there's 2 electrons and they take 1 each, and that's why we end up with 2 chlorines, each of them with an unpaired electron. Okay, and you'll notice here that the curly arrows that I've used, the arrowhead is only half an arrowhead, and a half an arrowhead means 1 electron has been moved. So 1 electron has gone over here, 1 electron has gone over there, and as a result we've ended up with two free radicals. So homolytic fission is when a covalent bond is broken and one electron goes onto one side, one electron goes onto the other side. Heterolytic fission, and I'm going to use the chlorine example here again, would be where a covalent bond breaks, but both electrons go onto the same side. So let's say the dot and cross, which are on this covalent bond here, both go onto one of these chlorines, okay? Now here I've used a double arrowhead, which means two electrons have moved. Now if that's the case, I'm actually going to end up with two different products. This chlorine here is taking back the electron that belonged to it to begin with, but it's also taking this extra electron, which originally belonged to this one. So this chlorine is going to actually have an extra electron at the end of this process, so we end up as a Cl minus ion. On the other hand, this chlorine did have this electron, but that electron's been transferred over to its neighbour. So this electron is actually one electron down compared to what it should have. So anything that has one fewer electrons than it should do ends up with a positive charge. So if the bond broke in this way, we'd end up with a chloride ion, a Cl minus, but also a Cl plus ion. Okay, and this is known as heterolytic fission. Now, I've gone into that in a lot more detail than what you need. The key thing that you need to be aware of is whenever you're dealing with a free radical mechanism, we start off the process with homolytic fission, where electrons go one to either side. All other curly arrow mechanisms, especially the ones that you've dealt with so far, whenever the curly arrow involves a double arrowhead, it means two electrons are moving, and that means any bonds that are broken undergo heterolytic fission. Okay, so when we go back to the request in this question, the type of bond fission that occurs, because in this curly arrow here, it's a double arrowhead, that is known as heterolytic fission. So that is the type of bond fission occurring in this process. Fission just means breaking, okay? So the type of bond breaking is heterolytic fission. Right, finally then for this task 11, the reason for the difference in rates of hydrolysis. So this is the point where we're comparing the rate of hydrolysis of chlorocyclopentane compared to the rate of hydrolysis of bromocyclopentane. And this is where you just need to know that a carbon to bromine bond is weaker and a carbon to chlorine bond is stronger, okay? That's just subject knowledge that you need to have in your head. So at this point we would say bromocyclopentane reacts more quickly because the CBr bond is weaker than the CCl bond, and that means the CBr bond needs less energy to break, and therefore it will break more quickly. Okay, so that explains the final bullet point which was requested in the question up here. So always at the end of a question like that, go back and double check the instructions that the question asked you to begin with, because we want to make sure that, you know, if we lose any marks, I don't mind people losing marks if they got something wrong or they don't know it. I don't like it when people lose marks simply because they've answered the first three bits of the question but then they forgot about the last bit. Okay, so always make sure you're nice and thorough in checking what the question's asking you. Okay, so that reviews tasks 10 and 11. I will be setting you some more tasks either later on today or earlier on tomorrow. So we'll be moving on with the next bit of our haloalkanes topic. Any questions about what I've just explained there, just send me an email as per usual. Okay, right, see you soon. Bye now.